All right, good morning, everyone. So as you can see here, I have an announcement that we're going to move the exam that was scheduled for this Thursday to Tuesday. I did that because, well, two things. We haven't finished rational functions. It's going to take us all of today. And that way we could spend Thursday doing a complete review. And I was going to send that review out to you this weekend. I didn't get that review out. I had to go out of town. So it all kind of works out better, I think, to do it on Tuesday, a week from today. That'll give you the whole weekend to prepare. So that is the plan. Are there any questions or concerns or comments or anything? Are we all good with that? Okay, let me see if that works. Okay, there we go, yeah. Okay, well, with that said, let's get into rational functions. And we started talking about these last class. And I showed you the graph of these things. And I thought that might be a good place for us to start, is for me to go back and just show you a graph of a rational function. Just to remind you, we were talking about probability and me getting struck by lightning and winning the lottery and all that stuff. You remember that? So here's an example. I'm going to give you something slightly different than what I did last time. Let's go plus 8, 7x. There we go. So there is just an example of a rational function. Very crazy things going on here. It looks like at the ends, it looks like the graph is flattening out towards something. And it looks like at certain values, we have our graph kind of like takes off, goes up and down. We do have, in this case, an X-intercept. So we've got all these different characteristics of rational functions that we have to be aware of. So I gave us a set of steps. I said, here are the steps, let's just write them down, and the next class we'll actually use these, and I'll tell you how to do each one. So let's go ahead and grab this and go to today's notes. Let me slap those in here, and we will set off and begin. All right, so the steps are, first thing we always want to do is find the X-intercepts. That would be any place. So an X-intercept is going to be a point or points on the X-axis, right? That's what an X-intercept has always been for us. Then we're going to go try and find these things called vertical asymptotes. And I'm going to abbreviate these VA from here on out. And what these vertical asymptotes are vertical barriers. Okay, I'm going to refer to them as barriers that force the function up or down. Okay, so let me go back to the picture that we had here of that rational function. And what I want you to notice, let me look at this one right here. Right here at the x value of -7. Do you see that? When x is -7, do you see that as my graph comes from the left, it's kind of dives down and just keeps going down here? But on the right side of -7, the graph is going up. So we have this vertical barrier. It kind of looks like we have this vertical blue, I'm going to put it in blue here. We have this blue line that is a barrier that when our graph gets to it, our graph is like, oh, I can't cross it. And the graph just like kind of freaks out and goes, oh, I'm going to dive down or I'm going to take off. So that is a vertical asymptote. So that blue one is what we call a vertical asymptote. And normally when I put them on our graphs, what I will do is I will not put it as a solid line. I'll put it as a dashed dotted line, because technically it's not part of our graph. It's just a reference for us so that when we draw the graph, we know not to go past that line and then to do this up or down thing when we get to it. Notice that we have another one over here at x equals 0. We have another vertical barrier or another vertical asymptote. So does everyone see that for this particular example, we have two vertical asymptotes, right? So the way that we go and actually find those is by setting the denominator equal to 0. So anytime we set the denominator equal to 0, we solve that equation. Whatever answers we get are going to be where we have vertical barriers. All right. Okay, so X-intercepts, vertical asymptotes, and then we get on to this thing called a horizontal asymptote. And this is probably the most confusing or most, not challenging, but the part that gets students tripped up most of the time. So I want to start by showing you what they are. Let me write down what they are. This is a horizontal line at the end of the graph which pulls the function towards it. I like to think of it as like a magnet. You know how magnets will pull two pieces of metal together? Well, if you look at our graph again, notice that we're just looking at the ends of this graph, just what's happening kind of like over in this region and in this region. So notice on both the left and the right ends of this graph, the graph appears to be getting pulled towards the x-axis, right? The graph is moving along here and it's getting closer and closer to the x-axis without actually getting there. You all see that? On both ends, that's happening. So we refer to that, the x-axis. In this particular example, the x-axis would be our horizontal asymptote. Now, I want to show you a different graph just so you can see that it doesn't always have to be the x-axis. So what I'm going to do is give you another rational function. Let's go x squared plus 1 over x squared minus 3x. Okay, yeah, let's do that one. Okay, and I'm going to hide the other one so we don't get confused by the two here. So notice on this rational function, we do have vertical asymptotes again, right? The vertical barriers, it looks like we have those. But notice on the edges, on the ends of this function, the function is getting pulled down, but it's not getting close to the x-axis. It's getting close to something, but it's not the x-axis anymore. It looks like it's raised up a little bit. And as I go out further and further, you'll see that it is not the x-axis. It kind of looks like it is, but it's not. I can exaggerate it a little more to make this more obvious to you. We go 8. Okay, so there. So look at that. It's flattening out, but again, it's not flattening out towards the x-axis. It's something else. And then we can also have this case where we don't even have a magnet that's pulling the graph down. See on this one, on both ends, it looks like it goes up and down. So this gets rather complicated, as you can see. Hopefully you can see that. So when it comes to horizontal asymptotes, there's a whole set of steps that we're going to have to do just to do that step. So what I'm going to do here is on the side, I'm going to tell you how to get the horizontal asymptotes. So for the horizontal asymptotes, I'm going to abbreviate that HA from now on. What you do, okay, what you do to figure them out is first thing you do is you compare the degree of the numerator to the denominator. And I already put that up there in the notes from last time, but I just want to put it on the side here, to the denominator. So when I talk about degree, I mean the highest power of x, right? So just for example, if I had x squared plus 1 over x to the third minus 1, let's say I had that was my rational function. The degree of the numerator would be 2, and the degree of the denominator would be 3, right? It's the highest power of x you see. So you're going to look at those two numbers and you're going to compare them. And there's one of three things that could happen. The first thing that could happen is that the degree of the numerator could be smaller than the degree of the denominator, which is what we have here, right? The degree of the numerator is 2. The degree of the denominator is 3. So the degree of the numerator is smaller than the denominator. If that happens, then the x-axis is the horizontal asymptote. That's what the horizontal asymptote is. It will always be the x-axis if the degree of the numerator is smaller than the denominator. So if I go back and I show you that graph that we had earlier, let me bring that original one here. No, I changed it. Oops. Yeah, no, that one will work. Let me zoom in on this. Okay, so here was the first graph I showed you. So I'm talking about this one right here. This is the function, oops, x squared plus 4 over, oh no, sorry, x plus 4. And then over x squared plus 7x, right? That one right there. Notice that the degree of the numerator, in this case, is 1, and the degree of the denominator is 2. And since 1 is smaller than 2, we know that the x-axis is going to be our horizontal asymptote. Does that make sense to everyone? Are there any questions on that? Okay, so that's the first case that we could have. Let's see, what would be the next case? Well, what if they're the same, right? What if they're equal to one another? What if the degree of the numerator is equal to the degree of the denominator? Well, this is the one that's the tricky one. If this is the case, then you're going to have a horizontal asymptote. It's going to be the leading coefficient of the numerator divided by the leading coefficient of the denominator. So let me explain this by going back to the graph I showed you a minute ago. So I'm going to go back. I'll put that back up so you can write that. And when I first showed you this one, let me see. Let me change that to an 8. There we go. So this one does have a horizontal asymptote. It is flattening out at the edges, but it's not flattening out to the x-axis. The question is, where is it flattening out, right? Where? Well, according to the note I just gave you, it should be, let me write down the function. It's 8x squared plus 1 over x squared minus 3x. So if we compare the degree of the numerator is 2. The degree of the denominator is also 2. Since they're the same, what we do is we go and we look at the leading coefficient. So the leading coefficient of the numerator is 8. So we write that number down, 8. And we divide that by the leading coefficient of the denominator, which is a number in front of x squared there, which is 1. And that means 8 is our horizontal asymptote. When we say 8, what we really mean is it's a line, y equals 8. So remember, if I have a line that's y equals a number, it's a horizontal line. So what I'm going to do is I'm going to have this computer graph that line, y equals 8. Let me see if I can change that. I don't know if I can change, I can change it to dash. There we go. Okay, so do you all see now that it looks like the graph is flattening out towards that dotted line? As I go further and further out here to the side, see it's getting closer and closer to 8. It's never going to get there, but it's getting closer and closer to it. And it's going and it's doing that on the other side also. Does that make sense? Okay, so that's the second case. If they're equal, you have to create this fraction out of the numbers. Now, the last case is if we have the degree of the numerator is bigger than the degree of the denominator. And in this case, oh yeah, by the way, right here where I had this up here, I'm going to put y equals that, or that equals y. That way you know that that's a horizontal line. when you draw it. But if the numerator's degree is bigger than the denominator, then you're going to have no horizontal asymptote. That means you do not have a magnet that's going to pull your graph down. So that means that the left side is going to go up forever, or it could possibly go down forever. We don't know. And the right side could go up forever or go down forever. We don't know. So in this last case, where the numerator is bigger than the denominator, the end behavior is going to be more like a polynomial where the sides go up or down. We just have to figure out which one it is. Okay, and that is how you find the horizontal asymptotes. There's only 3 cases that it could possibly be. So when I go back and look at this graph, let me see here. Let me change this one. So I'm going to change that one to x cubed. Get rid of the 8. Get rid of that. Get rid of that. So here is an example of a rational function where notice that we do not have a horizontal asymptote. Looks like the right side goes up and the left side goes down. Now, if we look at the actual function, x cubed plus 1 over x squared minus 3x, we'll notice that the degree of the numerator is 3, the degree of the denominator is 2. So the 3 being bigger than the 2 is why we have the ends doing what they're doing. Now, we're going to have to do examples, obviously, to get our heads wrapped around this. I'm just trying to lay it all out for us right now. So when we go to graph these, we'll have some idea of what they look like. Any questions? Okay, so we find the x-intercepts, which are going to be points on our x-axis. We find the vertical asymptotes, which are going to be these dotted vertical barriers that are going to force our function up or down. Then we find the horizontal asymptotes, which will be the magnets. We may not even have them, but we have to check to see if we do. Then step 4 is to put all this information onto a graph. So we're going to go put our x-intercepts there. We're going to put our vertical asymptotes there. We're going to put our horizontal asymptote there. We're going to have the whole picture set up. And then we're going to do this very tricky step called picking test points. And when we do a problem, I'll show you what this is. And then after we have our test points, we will sketch the function. Now, this sketching rational functions is by far the most difficult type of function to sketch in college algebra. It's the hardest one because it has so many things that you have to get right. So without further ado, let's do one, okay? So I'm just going to make one up here. Let's do f of x equals, let's go with 3x minus 12 over x squared minus 2x. All right. Y'all ready? Here we go. We have a lot of people here. I think that we have 20 people here today, which I think is because this was going to be the day before a test. So I think people were here because they want to make sure they understood what was going to be on the test. But I tricked you. You're here now, but you're going to, this is good that you're seeing this, all right? All right, so first we want to make sure we have to know we're dealing with a rational function. Like we have to know that this is a polynomial over a polynomial. So that's kind of not the first step, but it's kind of like the pre-first step. Victoria, your dog's messing with you or what? That's funny. Okay, so we realize it's a rational function. And so I go to the first step, which is to find the x-intercepts. And to find the x-intercepts, what we do is we set the numerator equal to 0. So I'm going to set 3x minus 12 equal to 0. And for this particular problem, that's just a linear equation. So we solve it the way we know how to solve linear equations. We move everything, we isolate the x, so we add 12 to both sides. And then we divide by 3 and we get x is 4. So I expect everyone here can do that. And let's just remember that this is going to be a point on the x-axis. Okay, that's what that's going to be. Now we move on to step 2. Step 2, we find the vertical asymptotes. So how do we find vertical asymptotes? we set the denominator equal to 0, right? So I will now set the denominator equal to 0. And hopefully you notice that that's a quadratic equation. So we have several ways to solve quadratic equations. And we've talked about this in this class already. You can try and factor it, or if all else fails, you can go to the quadratic formula. But this one factors. It factors pretty nicely because we're missing the constant term. And if you go back and look at our notes, when we were talking about solving quadratic equations, we had these special cases. And I said that if you're missing the constant term and all you have is terms with x's in it, then you can just do GCF. You can just pull out a greatest common factor. So here they both have an x. And then once you're here, you just set each factor equal to 0. And you have two equations to solve. The first one's already solved, x must be 0. The second one, you add 2 to both sides, you get x is 2. Now, it's very important that at this point you realize that these two answers, 0 and 2, are not points on our graph. These are our vertical asymptotes. So I'm going to remind us here that these are vertical barriers, right? They're not technically part of the graph, but they will help us draw the graph. So we're going to put those in there as vertical dotted lines when it's time, all right? Let's go to step 3. I'm going to try and squeeze step 3 in over here. For step 3, I need to find the horizontal asymptotes. So I look at the degree of the numerator. The degree of the numerator is 1, okay? That's the highest power on x I see there. The degree of the denominator is 2, and therefore the degree of the numerator is smaller than the degree of the denominator. And in this case, going back to the notes, whenever the degree of the numerator is smaller than the denominator, the x-axis is going to be our horizontal asymptote. So we're kind of in this first case here, case 1. So just from looking at that, that means that the x-axis is your horizontal asymptote. So we do have a magnet that's going to pull our functions down. But remember, this is only the horizontal asymptote only ever tells you what's happening at the ends. Okay, it tells you nothing about what happens in the middle. It just tells you what happens at the ends. It pulls your graph down. Any questions? All right, step 4. Time to plot all the information that we have so far. So I'm going to start to put this together into a graph. So the way I like to start this is I draw my x and y axes, give myself plenty of room. And the first thing that we know is that we have an x-intercept at 4, right? An x-intercept at 4. That's a dot. It's part of my graph. So my graph, I'm going to draw my graph in green, okay? So let's say that's 1, 2, 3, 4. I'm going to put a big old dot right there. Okay, that's part of my graph. Now I move on to the next thing I know. I know I have 2 vertical asymptotes. I have one at 0 and one at 2. Okay, so these are vertical barriers. So I'm going to do these in a different color. I'm going to do these in orange. At 2, I have a vertical dotted line that I cannot cross. When my graph gets close to that dotted line, the graph is either going to take off up or it's going to take off down. I don't know yet which it's going to be. It's up or down, but I'm not sure yet. Also, I have another one at 0. Now, since 0 is the y-axis, it's kind of hard to draw a dotted line on top of a solid line. So one thing that I've done in the past is instead of doing dashes that are straight up, I just do little diagonal dashes. And that way, that's a lot easier when you're on, on paper and pencil, because you can't really tell the difference. But that way you can really kind of make out that you have a vertical asymptote there. Okay, Any questions? What's next? We have a horizontal asymptote, right? We have a magnet that's going to pull our graph down. It's the x-axis, right? So here's the x-axis, but it only pulls my graph down at the ends. So this is a very important step, okay? When you draw, I'm going to draw a dotted line, okay? Because I want to represent where it's going to get pulled to, but I'm not going to draw the dotted line anywhere in the middle. Okay, because the horizontal asymptote has nothing to do with what's going on in the middle. I'm only going to draw it at the edges. So here's what I'm going to do. I'm going to do a dotted line over here on that edge and a dotted line over here. And what I need to remember is that as I draw my graph is going to have to taper towards those dotted lines. Okay, that's all the information we have, right? Unfortunately, this is not enough information to draw the graph. We need a few more pieces of information. Like, for example, just think about this. The graph could go and turn up right here, right? It could do that. It could then come down and maybe flatten out like that. That's perfectly logical that it does that, right? It goes through the x-intercept, it goes up, it goes below, and then gets pulled back as a magnet towards that line. But I don't know if it does that. It could do this. It could go at that dot. It could go up over here, but it could have like bounced off and then come back down. Could have done that. I don't know. And there's nothing to say that it didn't go down instead of up and then come up here and flatten out. So there's a lot of things that are uncertain still. And so to remove that uncertainty and to be able to figure out exactly which case it is, what we have to do is pick test points. So what you do to do test points is you get to choose any points that will help you graph this with more precision. So what I do is I start from the left and I look in this region over here and I say, okay, look, I don't have any information about what's going on to the left of this vertical asymptote. So I'm just going to pick a random point to the left over there, any number I want. I'm just going to pick, to make it easy, I'm going to pick -1. And I'm going to circle it. That's going to be a test point. All right? So I've picked -1. Let's just put that on the back burner. Now let's understand that we don't know anything about what's happening between these two vertical asymptotes. So I'm going to pick a test point between those two. What would be a good number between those two, these two x values, 0 and 2? I'm going to start calling on y'all soon. So, okay, Victoria's got the number 1 up. So 1 would be a good number there. Now, I do not know what's happening between here and look, I'm going to stop right here at 4 because I'd like to know what's happening between these two. Something in here. So I'm going to pick 3. And then I also want to know what's happening between here and the rest of the way. So I'm going to pick some random number over here. So I'm going to pick 5. These 4 test points that I picked are now going to give me the rest of the information I need for this graph. Are there any questions on how I picked these test points, why I picked them, why I'm not picking more, or why, could I have picked less? Are there any questions on that? I almost look at it like there's like a couple of regions, like there's this region here, there's this region here that I don't know. There's this region between the vertical and the x-intercept, and then there's like this final region over here, right? So we had like 4 different regions, and so we picked 4 different test points. Every problem is different. Sometimes you only have 2 test points. Sometimes you only have 1 test point. Sometimes you'll have 6 test points. It all depends on the information you have. Okay. Now, what do we do with these test points, right? Like that's the next thing. Like, what do we actually do with them? Well, what we want to do is be able to know what the function is doing. So this isn't good news, but it's what you have to do. We have to go back up to the original function, which is this right here. And we need to plug these test points in to that original function. Okay, so that means I have to plug in -1 into that function. I've got to plug in 1. I've got to plug in 3. And just to save some space, I've got to plug in 5. So all 4 of these points have to get plugged into the function. And what you're looking for is to determine whether or not your answer is positive or negative. Okay, so let's plug in -1. Let's see what we get. 3 times -1 minus 12 over -1 squared minus 2 times -1. So you got to be real careful with your signs here. You should get -15 on top. And on the bottom, you should get +3. Because you square the -1, that becomes +1. But then -2 times -1 is +2. So this is going to be 1 plus 2, which is 3. Now, I have a negative divided by a positive. So my answer is -5. But like I said, the only thing I'm really concerned about is that it's a negative number. Now, here's why this is so vitally important to us. What that tells me is that when I plug -1 into the function, it's spitting out a number that's below the x-axis. So it's down here. I don't even care how far down it is. I know it's -5, but I'm just going to put it right there. So do you all see now that I have another point on my graph? So I've got more information now, right? And I've got to do that for the remaining 3 points. And, you know, this is, I told you, it's tedious, right? This graphing rational functions is tedious. If there were a shorter way to do it, I would tell you, but this is it. So when I do that, I get, let's see, -9 on top. And on the bottom, I'm going to get 1 take away 2. I get -1 there. A negative over a negative is positive. See, now I'm not even going to care about the fact that it's +9. Just going to put a plus sign there.
Wait, sir, I have a question.
Yes.
So on the f, the first one I did, f of -1, the denominator, wouldn't it? I don't know if I'm doing it wrong, but I got 4 because I thought they were both positive. So then you would just add.
Yeah. So when you square -1, you get +1, right? And then you have minus. Let's just multiply those two together. Those two together gives you -2, right? So you're not subtract. You're multiplying those two and then subtracting it. So when you multiply those two, you get -2. Then you subtract a negative. That means plus.
Oh, so it's 1 plus 2.
Yes.
Oh, okay.
Got it?
Thank you.
Good.
Yeah.
No, thank you for asking a question. It was getting kind of lonely here. All right. So at -1, we had a point down here. And then at +1, we have a point that is positive, an output that's positive. So I'm just gonna put a dot anywhere up here. Again, I could go all the way up to 9, but I don't even care about that. I just need a little bit more information to graph this function. So that's good enough. Now we do the same thing for 3, right? So you plug in 3 times 3 minus 12 over 3 squared minus 2 times 3. So we get 9 minus 12, that's -3 over 9. 9 minus 6, which is 3, which is going to give us now a negative number. So when I plug in 3, I get a negative answer. So when I plug in this 3, down below somewhere, oops, I'm doing it in green, down below somewhere, I have a dot. Last one, let's plug in 5. So we plug in 5, get 3 times 5 minus 12 over 5 squared minus 2 times 5. 3 times 5 is 15, take away 12, you get 3. And then 25 minus 10, 25 minus 10, come on, 15. That's a positive number. 3 divided by 15 is positive. So I'm going to put above there just a dot. All right, any questions on this?
So just to clarify, your points are either just positive or negative, and you can pick whichever you want.
Well, you can't pick whether or not they're positive or negative. You can
Yes,
where you put it.
right. So
Yeah.
the number itself doesn't matter. It just needs to be either positive or negative.
Yeah, the thing is, you need to know whether or not you're above or below the x-axis. Let me go back to, remember when all we had was this point. I'm going to highlight it in green. Remember when all we had was that point? And I said, hey, you know, it could do this, right? It could do that.
Right.
It seems like that could be. Well, now I know it can't. And the reason I know it can't is because to the left of 4, I've got to be down here, right? I've got to be below. So I
Okay.
can't go up. And then when I get to the right of 4, I have to be up here, not down below. So these points are just to give us just a little bit more information so we can start constructing the picture. See, now I know that these points are going to have to connect, right? These have to connect to one another. And yeah, well, let's do that step now. But I think I answered your question. We just care about whether or not they're above or below. The value doesn't really matter.
Okay, thank you.
Any other questions?
Yes, I missed the part where you put all these dotted lines. I'm having connection issues.
Okay. Okay, so yeah, I think, why don't we get to the next example and I'll restate that. I don't want to go back to what they are right now because we're right in the middle of this, but I will restate it again. And remember, I'm recording this and I'll put it up on YouTube if you need to go back and watch that first part.
Okay, thank you.
Okay. All right, so now look, at this point, we're back to like first grade. We're just going to be trying to connect the dots. Okay, that's all we're going to be trying to do, connect the dots. But we have, it's more than first grade. I'm not trying to dumb this down. I'm just saying that it is connecting the dots, but we have to pay attention to all the pieces of the graph and what they mean to us. So I always like to start at the actual point that I have, that I know I have on my graph furthest to the left, which is that point in blue. That point I know lives on my graph, right? For sure, that's on my graph. Now, I have to imagine if I draw to the left, don't draw this, but if I go to the left, what happens, right? Like what actually happens to the graph as I go to the left? Can I just do whatever I want over here, or am I forced to have to do something? So what am I forced to have to do?
You have to go towards the x-axis.
That's right. We have a horizontal asymptote right there. We've got to get closer and closer to it, right? That's the behavior. So what I'm going to do is I'm going to draw up towards that. I'm not going to cross it, just get closer to it, draw a little arrow, and there now I'm representing that my graph is getting pulled towards that horizontal asymptote, right?
Wait, sir, how do you know how far up or how far down you go on those points? Like the test points that we found.
Yeah, that's completely up to you. So do you remember when we were doing polynomial functions? Let me get back to a polynomial. Do you remember when we were doing these? Last class. Do you remember when we were doing these polynomial functions that we were doing bounce cross? And I told you that it did not matter if someone drew it like this. It didn't matter how high up or down. It's just to get a general feel of the graph. Like these should both be, like here, they should both be above the x-axis. Here, they should both be below. But like everyone's picture is going to be a little different, right?
Oh, okay.
It's the same story here. Everyone's graph is going to be slightly different. Someone else might do this. Someone else might get crazy and be like, oh, I want to come down here, then back up. All of those would be acceptable. As long as you start at that point and you get closer to the x-axis, everyone's going to have the freedom to draw it how they want.
Okay.
If you want to know the shape of the graph, like in more detail, you have to take calculus. In calculus, we actually get into like, no, we need to be more precise. For us, we're just getting general shape.
Okay, thank you.
Good question. So now I'm going here, we've flattened out. Now, from that same blue point, I need to try and draw to the right. But as I try and draw to the right, I see that I have a vertical barrier, right? My vertical barrier is right here. That vertical barrier is telling me, nope, you can't come through. All right, you're not allowed to come through. So you either have to turn up or turn down. So I'd like for someone to tell me whether or not I'm going to turn up or down. And like, do I have a choice, or does it have to be one of them? What do y'all think? So I'm trying to draw to the right and I have a barrier in my way. Go ahead. I thought I heard someone say something.
Would you turn up since the next point is like on the positive?
Okay, so that makes sense. You're seeing that they have a point up here, so maybe I need to get up to that point, right? So I turn up. Well, let's see what would happen if I turned up. I'm not allowed to cross, okay? I cannot cross that dotted line. If I turn up, what happens right there? What did I just do?
You would need to have another X-intercept.
That's right. See, right there, I would have had to have crossed the x-axis, which means that I would have had another x-intercept, but I don't. The only x-intercept I have is this one right here, that blue one at 4. So if you turn up, you're going to create an x-intercept that you don't have, which means you have to turn what? Down, okay? This has to go down. So this is not, it's not a coin flip. It's not a 50-50 flip a coin, it's up or down. It has to be one or the other, but you have to be thinking about why. Is everyone clear that I cannot turn up here because I create an x-intercept that doesn't exist? Okay. Now, I'm not sure who said it, but someone had mentioned, well, wait a minute, we have a point up here, right? Well, as soon as you get to a vertical barrier and you finish drawing what's happening to one side of it, what you do is you go and you jump across to the other side and you just go to the next point that you know. So I know that this point exists. And so I need to draw it to the left and I need to draw it to the right. Okay, so from this point, what happens if I try and draw this to the left? Well, there's the barrier again, right? I'm on the other side of it. So is the barrier going to force me to go up or down?
Up.
Up. Why can't I go down?
You would have to have more x-intercepts.
That's right. I would need another x-intercept right there, which I don't have. I only have one x-intercept, so I can't turn down. So this is like a process of elimination. You know you can't go down, so you must turn up. It goes like that. Now you try and do the same thing to the right. And as you draw to the right, what happens? Oh, there's a barrier in your way again. But you can't go down. You have to go up, right? So I know I'm going to turn up here. It's almost going to look like a little parabola in there. It's weird, but that's the way it is, okay? That's what the function is doing. Now is a great time to ask a question if you have one. I know that these are complicated when you first see them. So I've drawn everything in between those two vertical asymptotes. What I have to do now is pick up my pencil, go to the other side of this vertical right here, and go grab the first point that I have, which would be this point here in yellow. I need to draw to the left and to the right. So let's start to the left. To the left. Oh, there's a barrier. Which way am I going to have to turn? Can't turn up, right? Same thing. And you can't do this. You can't like turn back. Okay. Once you start going to the left, you got to keep going to the left. So this has to go down, doesn't it? Like that. And then as I draw this point to the right, what do I have to do?
Meet the x-axis.
Yeah, see now it's like first grade. Now I've got a couple of dots that I can connect. There's nothing in my way, right? There's no vertical barriers. I connect here, I come to this one, and then as I start to draw out to the right this way, I say, oh, wait a minute, there's that horizontal asymptote. I've got to start flattening out towards that. And we are done. That only took 45 minutes. wow, right? There's a lot going on here. So what I'd like to do is I'd like to graph this on the computer. So this was 3x minus 12 over, oops, x squared minus 2x. There we go. Oh. So here's the graph. Here's the graph. All right. Here's our graph. Here's the computer's graph. So ours is not terribly bad. We have the x-intercept. We have that it drops down, flattens out. We've got that little U shape, the left side. I mean, I think we've done a pretty good job, right? I think we've done a pretty good job. All right, let's do another one. Let me think. Hold on. All right, let's do that. Okay, first of all, it's a rational function, right? First step, I'm going to go a little bit faster through this. First step is x-intercepts, right? How do we find x-intercepts? We set the numerator equal to 0. That's a quadratic equation. So I look at that and I realize, you know, I'm missing the constant term. So I can do GCF. I can pull out a 4x. Oh, crap. I just realized something. Go back up to the original function. Let's change this. Hold on. Change that to minus 24. Make it minus 35. Sorry, everyone see that? I'm changing the problem right here to minus 35. That doesn't change anything we've done so far. Okay, so now we set these both equal to 0. You get two answers, 0 and 3. So you're just setting each of those equal to 0. Is that all right? Those are points on our graph. And now we move on to the next step, which is the vertical asymptotes. The vertical asymptote, we're going to take the denominator and set it equal to 0. Now, here you have two options. You can factor it, or you can use a quadratic formula. I'm not going to go through the process of this because it'll take too long. I know a lot of you would probably do quadratic formula here because you've gotten kind of, a lot of you said that you favor that formula. I'm going to do it, just to be quick, I'm going to do it by factoring. This is x. Oh, shoot, I messed that up too. Man, why did I mess that up so bad? I guess it just is like a Monday. I want this to factor nicely, and I just realized now that I made it that it's not going to. So let's fix it. I apologize. Let's change this 3 to a 2. Everyone see that? I'm going to change that to a 2, change that to a 2. Now it will factor. It should be x plus 7, x minus 5. Just double check that. Okay, so you'll get two answers, -7 and +5. My apologies. Again, you could use a quadratic formula to get that, all right? Now, these are your vertical barriers, right? Vertical barriers. So this, if you think about it, this is gonna suck, okay? We have two x-intercepts, we have two vertical barriers. This is looking pretty complicated. Third one, we need the horizontal asymptote. So what's the degree of the numerator? 2, right? Degree of denominator? 2 also, right? So what happens when they're the same? When the numerator equals the denominator? This is the one that's tricky. Think about it for a second. I gotta turn the heater off. It's too damn hot in this office. Okay. So what happens here? What do we look at when the degrees are equal? What are we looking at then?
You divide
Leading
it.
coefficient.
Leading coefficient of the top one, which is 4, divided by the leading coefficient of the bottom one, which is 1. And that gives me 4. So y equals 4 is my horizontal asymptote. Any questions? Time to draw it. I will start with my x-intercepts. I have one at 0. 1, 2, 3. I have one at 3. I have a vertical barrier at -7. 1, 2, 3, 4, 5, 6. Oops, 7. Here's -7. Vertical barrier out here. And I also have another one at 5. 3, 4, 5. Vertical barrier out here.
So the -7 should be 1 to the right.
Did I mess that up? Okay, so I have, let's see, 1, -1, 2, 3, 4, 5, 6.
Oh, I thought there was one between the.
I messed up. I didn't erase it. There we go.
Oh, okay. Sorry.
Yeah, it's okay. And you know what? On your graphs, it doesn't have to be perfect. Like I would accept this if you just did like, okay, -7 somewhere over here, 5 is over here, and then 0 and what was it, 2 or 3 or something? Right, 0 and 2. Like you don't have to have it marked out perfectly as long as everything's in the right like position.
Okay.
Okay. All right. Now we still have one more thing we haven't put up here, right? And that is the horizontal asymptote. So I'm going to do this. Watch how I do this. I'm going to go up. I'm going to just say that that's 1, that's 2, that's 3, and that's 4. Then I have my horizontal, right? But do not put your horizontal in here. It's only what's happening at the edges. So watch the way I'm going to do this. I'm going to go like, I'm going to just follow like 4 units high. I'm going to put it way out here. I'm going to just put my dotted line out here. And then I'm going to do that on the other side. Way out here, I'm going to put a dotted line. So you see how I'm not putting a dotted line through the middle? The reason I don't is because I promise you, if you put a dotted line through the middle, it's going to screw you up when you go to try and graph it. You're going to think that that dotted line, you can't cross it, and you're going to start to mess things up. Just do the dotted line on the edges. Now, the verticals have to go where the verticals are. Like those, you can't change them. They're fixed. Questions? What's our next step? What's our next step?
Test points.
Test points. Okay, somebody give me the first test point they want me to put down.
-8.
-8, good. So you realize that you need something over here, right?
Mm-hmm.
You need something to cover this region right in here. Good. Now also notice when I put -8, notice I did not put a dot there. I've seen students do that before. They're like, oh, I'm going to pick -8, and they put a dot there. That's so dangerous because if you put a dot on the x-axis, then later on when you're drawing, you might think that that's part of your graph. So that's why I always put the number and I circle it. And that way I know that's my test point. Okay, somebody else want to give me the next test point?
-1.
-1, that will work. Who said that?
Victoria.
Victoria, could I have picked -2?
Yeah.
Yeah, -3, -4, anything in that region would have worked. All right. Someone else give me the next test point that they want.
2.
2, okay, 2 will take care of that region. Someone give me another one.
6.
6, good. 6 will take care of this region. Do we have them all?
Don't you need to have one between the 3 and the 5?
You do. You need one more. So this 2 that we picked, that 2 covers everything between here and the 3, but we still need something between the 3 and the 5. So although all those test points we had done were correct, we need one more right there. That will cover all the regions. Now, here's a little tip for you. How many test points do we have here? How many do we have? 1, 2, 3, 4. We have 5 test points, don't we? We have 5 test points. How many x-intercepts did we have? How many did we have? We had 2, right? How many vertical asymptotes did we have? We had 2, right? That's a total of 4. You will always have one more test point than you do vertical asymptotes and x-intercepts added up. So if together you have 2 x-intercepts and 2 verticals, that's 4, then you should have 5 test points. If you had 3 x-intercepts and 2 vertical asymptotes, that would add up to be 5, so you'd need 6 test points. If you go back to the previous example, we had 1 x-intercept and we had 2 verticals, that's 3. So we should have had 4 test points, which you can see 1, 2, 3, 4. Okay, so that's just a little rule of thumb that helps you get through the problems. So we have our, here in this case, we've got our 5 test points. And now we got to plug them in. That's going to suck, right? It's going to suck, but it's the way it goes, all right? So in an effort to save time, I'm actually not going to go through each one of them. I'll do one of them, but that's it, all right? So I'll do the first one. We've got, this is our function right here, and I've got to plug in 5 different things to it. So if you plug in -8, you would have 4 times -8 squared minus 12 times -8 all over -8 squared plus 2 times -8 minus 35. And then I'd have to figure that out. So 8 squared is 64. 64 times 4. What's 64 times 4?
256.
256 minus, but that's a minus, that's plus. Well, here's what I can say. I don't even care what that number is. I can tell it's going to be a positive number on top. And then on the bottom, I have 64, take away 16, take away 35. That's a positive number on the bottom. And a positive divided by a positive should be positive. So that means that over here at -8, I'm going to put a dot above the x-axis, and it doesn't matter where. Okay, so I'm just going to choose to put it here. Someone else might have put it up here. Someone else might have put it here. It does not matter. I'm going to put mine right there.
I have a question.
Yes.
On the test, will you want us to show our work for all of that, or could we plug it, like write out the number plugged in and then put in a calculator and show you that they're both positive? Like
You can use your calculator for this step. Okay, that's perfectly fine with me. Just if you're not going to write these steps down, and let's say you go through this and you just say it's negative and it's wrong, well then it's wrong, right? I mean, So just be careful is what I would say. Because this is tedious, right? To have to plug 5 different points in, this is tedious. But it is what it is, right? It's the nature of the beast here. Okay, now at this point, you would have to continue with the 4 other points. I'm not going to, but I am going to tell you what you would get, all right? So if you plugged in -1, you would actually get a negative number. If you plugged in +2, you would get a positive number. If you plug in 4, you're going to get a negative number. And if you plug in 6, you're going to get a positive number. I'm going to put it way up there. Now, do you notice how they switched each time? Like we found the first one that was positive, and then the next one's negative, then positive, then negative, then positive. So you might be sitting here going, oh, great. All I have to do is find one of them, and then all the others switch. Not the case. It doesn't always do that. So you have to test each one.
Wait, sir. So I know like when you first plotted the -8 point, and you said like you could go as high as you want. What's the point of the horizontal, or what's the point of the line across it if you like can't pass it?
Well, okay, so I'm glad you asked that question. The vertical asymptotes, the vertical barriers, you cannot cross, okay? Horizontal asymptotes are not like those. You can actually cross them. You just have to get closer to them as you move to the sides. That is exactly why I don't have you drawing it all the way across. Because if you try and draw it all the way across, then you will be crossing it several places and you're going to get confused. So let me finish this, and then what I'm going to do is after I finish drawing it, I'm going to draw it a different way, the way someone else might have drawn it. And you can see the subtle little differences in our graphs. Okay? So I've got all my points. I start here at the left, and I'm just going to talk through what I do now. To the left, I must get closer to the magnet. To the right, I see a barrier in my way. I must go up. I cannot go down because then I would cross the x-axis. I can't cross the x-axis there. Once I've got that region, I jump and I start looking for my next point. Here's my next point right there. When I get to this point, I start to draw to the left, and I'm like, I'm just having a great time. There's nothing in my way, nothing in my way, nothing in my way. And then here comes the barrier. The barrier is going to force me to go down. Again, I can't go up because I will cross the x-axis, so I can't go up. I have to go down. As I draw from this point to the right, I realize I have to connect some dots. So I'm back in kindergarten. I'm connecting that dot together. I'm going up. I'm going to connect to that dot. I'm going to connect to this dot, connect to this dot, and then I go to the right. Up, there's a barrier. Have to go down. Can't go up, right? If I go up, I cross the x-axis. So that whole middle piece was actually really nice, like everything connected together. Then I jump over the vertical. I go to my next point, which is way up here. And I'm going to draw to the left. And there's that vertical barrier. It forces me up. Again, I can't go down because I can't cross the x-axis. And then to the right, I've got to flatten out. That's my picture. Now I'm going to draw another version of this using red. So if I would have had red, I still would have had these x-intercepts. But let's say when I did my test points, I would have done the one at 8 way up here. Let's say I would have done the one at -1 here. The one at 2, let's say I put it way up here. Let's say the one at 4 I put right there. Let's say the one at 6 I put there. So what would this person's graph look like? To the left, they flatten out. To the right, they go up. From here to the left, they go down. Then they have to go connect the dots, connect, up, got to go down. Then to the left, got to go up. To the right, got to flatten out. Both the green and the red would give you a perfect grade on that problem. They both are doing the exact same thing, even though they don't look exactly the same. They have the same exact behaviors. Now, does that help clarify that question earlier about what was going on, like what's going on over here with that dotted line? Does that show you that there's some variation that you're allowed to have?
Mm-hmm.
Yeah.
Okay.
I had a question. So how did you know how to go up and down again?
Okay. Let's start right here. Let me get rid of the red one. So right here, we're starting on this left side again. Go to that dot. To the left, you have to go to the magnet, right?
Mm,
Now to the right, I either have to go up or I have to go down, right? I cannot go down because if I go down, I will cross the x-axis right there. And the only place that I'm allowed to cross the x-axis are these 2 points, right? Because we went and we saw it. We said the only x-intercepts we have are at 0 and 3. So if you go down, you're creating an x-intercept that does not exist on your function. So it can't possibly be that case. Does that make sense?
yes.
Okay. And so when I got, let me just get rid of the red one here. When I got to this point, the one in green on right here, when I was drawing to the left, I'm just like, oh, barrier, cannot go up. See, I create that x-intercept. So I have to then go down. So I have to go, okay. And look, literally, you could do whatever you want in here. I'm not going to take off. So if you want to be like funny, you can do that. But then you eventually have to go down. All right.
Mm, okay.
I mean, it doesn't look like that in real life. It is more smooth and just kind of drops like that. But does that help answer the question?
Yes. Thank
Okay.
you.
All right, let's go look at this function. Let's look at this function on the graphing software and see how good ours is. So we have on the top, we had x squared. Wait, was it x squared? 4x squared. 4x squared minus 12x. And on the bottom is x squared minus 2x minus 35. Wait, hold on. That isn't right. It better not be right. Plus 2x. Okay, it was plus 2x. Boy, that plus makes a huge difference. What the hell? Oh, I'm zoomed out. Okay, sorry. I was zoomed too much. Let's see. Does that look like ours? Let me graph something here. Let's graph y equals 4. Let's graph x equals, what were our verticals? They were -7
7 and 5.
-7 and 5.
and 5. Okay, so let me just change something here. I want to change this to dotted, make it real dotted. This to dotted and orange. This to dotted and orange. Yeah. There we go. So now you can kind of see we have our 2 verticals. There. That's the true graph. Here's ours. I like ours better because it took time and it took effort, right? So we have that little U shape. We've got that, right? We've got this. Ours doesn't look as good, but it's still the U shape. We know that between 0 and 3, we're above the x-axis. We've got this thing over here, this thing over here. We're good to go. Okay, so that's it. Class is pretty much over. We've done 2 problems. So now that you see this, you see that on the exam, I can really only give you like one of these realistically, right? But that means you're going to need to be able to do it, right? Like you can't get stuck on it. So the next exam is going to cover quadratic functions, polynomial functions, and rational functions. So what I'd like to do with the last 5 minutes is I want to give you a couple of problems to look at between now and Thursday. And that way on Thursday, you can come in and ask some questions like, hey, I had some trouble on this. You know, so this is kind of like an exam review because it's realistically the number of problems you're probably going to see on the exam. It's going to be like 3, maybe 4 problems at the most, right? So the first thing would be for you to sketch. This is all about sketching. sketch the function f of x equals, let's say, negative 3x squared plus 12x plus 7. Number 2, same thing, sketch f of x equals 4x squared minus 3x minus 11. Now for these, just as a hint to you, these are parabolas. And since they're parabolas, I expect you to go through the steps for parabolas, which is like, does it open up or down, vertex, quick sketch, x-intercepts, y-intercept, draw the picture. Okay, so you want to follow the steps for those. The next one, now we're to polynomial functions. So something like x to the 5th minus 7x to the 4th minus 8x cubed. And then maybe something like x to the 6th minus 5x to the 5th yeah, let's just do that and see how you do with that. Giving you a variety, like this is not how long the test is going to be. All right, I'm just trying to give you some variety for practice. I think that'll be good for you. How are y'all feeling about this test coming up? All right, or no?
No.
No. X to the 5th plus 5x to the 4th minus 9x to the 3rd minus 45x squared. Okay, so these are polynomials. We had a set of steps to sketch those, right? You go, you figure out, what's the degree, what's the leading coefficient, find your left and right hand behavior, find your x-intercepts, and then we talked about the touching and the crossing, right? And then we draw our picture. Okay, so that's numbers 3, 4, 5, and then 6, 7, and 8. I'll make all these rational functions. So f of x equals, we'll start off with a pretty basic one. Okay, let's see, next one. Give you one more. No, I think that's enough. I think that's good. I think that's good. Okay, so both of those are rational functions. And you'll follow the steps that I gave you last class and completed this class. I'll also email you all, or I'll put it in the chat right now for you. I'm gonna send today's notes. What's today, the 27th? 7? Yeah. Okay, so in our chat right now, I'm going to go ahead and send that. Are there any questions while I'm getting this here?
I I think you had mentioned it like another class, but are we able to write these steps down for all three on a paper and have that with us?
Absolutely. On this test, you are going to be allowed to have your own formula sheet that you make. And on that formula sheet, it can be just a standard, standard sheet of paper, front and back. And what you're going to put on there are all the different steps for graphing parabolas, polynomials, and rational functions. The thing you cannot have on that sheet is just worked out problems. So you can't just like take the problems I just gave you, do them all on a piece of paper, and then say that's your formula sheet. You can write down steps, procedures. You can write yourself little notes like, hey, remember that the magnet, only tells you what happens at the ends. Write whatever you want. Just don't work any problems out. Okay, so I would start getting that together as you're going through this, and you start to realize the things you need to know. I would start creating that cheat sheet now. All right. Any other questions on that?
Quick question. Can we write like not problems, but like equations that we'll forget? So like for an example, sorry, I'm trying to pull it up right now. I believe it was the
Quadratic equation? Or the quadratic formula?
yeah, like for an example, the quadratic function one, like the minus b, all that. Like we can put in the letters and everything.
Yep.
Okay.
Yeah, you can have any formulas or anything like that. The only thing I don't want to see is you like working out an entire problem and then using that as your reference during a test, because to me that's just too much.
Okay.
But everything else, all the different formulas, all the different steps. If you need to remind yourself how to do AC method, you can write it down in words. Be creative about it. Make sure that it's going to be useful to you. But you also know like what's overboard, when you're putting more than you should be, I guess. There's no worked out problems. You'll be fine. Are we good? It's 10:48, so we're past due. I see you on Thursday. Please come with questions, all right? Because there's no way that I'll be able to do all these problems in one class. Like there just won't be enough time. So I'd like for you to have done all these, and maybe I can just like put the solutions out there for you and we can talk through it. But I will see you Thursday. Have a good day.
The test is on Thursday, right?
No, the test has been moved. So this was at the beginning of class. The test has been moved to Tuesday. All right, today we finished rational functions. We're going to review on Thursday. The exam will be on Tuesday.
Oh, okay. Thank you.
Okay. That'll give everyone the weekend to get ready.
Bye, sir. Have a good day.
You too.
Alrighty, thank you, sir.
Thank you.
Have a great day.